Okay, so hi everyone. Welcome again to physics/chemistry/computer science C191. Thanks so much for taking the class. I'm really looking forward to it. I hope you guys are too. And yeah, as I said in the first attempt, these are very weird times. For me, it's my first time teaching a class. I was a grad student at Stanford back in June this year. It's also my first time being involved in teaching a class over Zoom. So yeah, any feedback you have about online teaching or anything else, please, it will be appreciated. What is this class? What is Physics Chemistry CS C191? Why should you care? So why C191? Well, I'll give you, it's quantum information science and technology is what it says on the tin, but I'll give you a couple of reasons to care about it. The first is that quantum technologies in general are really, there's a lot of hypey buzzwords about the field. One of them is that it's a 21st century revolution in science, what we're able to do. And as with all hype, you shouldn't believe it, but there's normally some truth to it. Deep learning, for example, the hype is crazy, but they have been doing some pretty cool stuff. And it is fundamentally true that the control we have over quantum systems and the things experimentalists are doing these days are completely insane and crazy. So just give you some examples of quantum technologies. The sort of, the monster, the end vision is a general purpose, error corrected quantum computer, right? And there's a lot of hype about this Google achieving quantum supremacy and so on. Yeah, they're doing really amazing things. It's incredible what they're able to do, but as a practical matter, really practical general purpose quantum computers doing things like factoring prime numbers and even stuff like simulating quantum mechanics is very long way off. We're talking decades at least before cryptography is being revolutionized, because ordinary public key cryptography can just be broken and so on. So yeah, it's from an experimental point of view, that's not going to affect your lives anytime soon. But there's a whole host of other technologies that really are on the horizon of being practical. So just to give you some examples, you have quantum cryptography, not to be confused with hacking cryptography using a quantum computer, which is a long way off, but using quantum mechanics in order to as one aspect of a cryptographic system to keep things secure. That's something that's happening now. It's something we'll cover in this class, exactly, some simple ways of how you can do it. There's also quantum sensing. It's becoming a big thing. There's all these bounds. There are classical bounds on how accurate you can measure certain things that using quantum mechanics, using quantum effects like squeeze states and stuff like that, you're able to violate these bounds. It's happening in all sorts of stuff. I think the upgraded version of LIGO, the gravitational waves detector, stuff like that are going to be using it, but also all sorts of more practical things to get used in everyday lives. Final one I'm going to mention as a near-term thing is quantum simulators. Quantum simulation. So this sort of sounds similar to quantum computers. The difference is, rather than trying to build some completely general purpose quantum computer that can do anything under the sun, like a sort of classical, the quantum equivalent of a Turing machine, you just want design something that's designed to simulate a particular system, right? You engineer it specifically to do a good job at that one task. And that's obviously a lot easier. So all of these tasks collectively are really near future things that we can get excited about. Okay. There's a second reason to take this class. least from my point of view, which is that it's going to be a class that really gets to the conceptual heart of sort of the quantum part of quantum mechanics, without sort of the distraction of all the mechanics that you normally have in a physics or a chemistry quantum mechanics class. So if there's one thing people know about quantum mechanics, it's that it's weird, right? Yeah, there's this if you know anything from pop sci about quantum mechanics, that is what you know. So anyone want to give any examples of ways in which quantum mechanics is weird? Yeah, this is yeah, if do people with their hands up have questions, have answers for this, or do they have their hands up already and it's just been sitting there? So Jan, for example, do you have your hand raised for a reason?
Oh no, but I think it must have been a leftover.
Okay, if you still, Hyung Song and Jerry, I think, also have their hands raised at the moment. Yeah, okay, let me list some ways it's weird that you may or may not have heard of. There's the famous measurement problem that we'll talk about already today. Right, that when you do measurements, the outcome in quantum mechanics is not determined in advance in some sense. There's things like, there's the double slit experiment, a particle being in two places at once. It's always pretty crazy. There's this sort of idea you sometimes hear that quantum mechanics involves spooky action at a distance. There's the uncertainty principle. It's very closely related to the measurement problem, that you can't, just in principle, can't know sort of every property of a particle at the same time. Yeah, I think that'll sort of do for now. So there's sort of one underlying concept that in fact unifies or is really pretty central to all of these things, which is this famous idea of entanglement. And entanglement, just very fundamentally, is really all about information. So if you want to learn about it, then definitely a quantum information class is the place to learn about it. And in fact, it's one of those things that somehow barely gets talked about at all in standard undergraduate quantum physics classes, which is just totally crazy to me. So yeah, if you take this class, you will know a whole load about entanglement. So just as the syllabus is online with sort of all the details about what we're going to cover in the class, but just very roughly speaking, we're going to have about 4 lectures that are just going to be an introduction to QM, to quantum mechanics. And that's going to culminate in the 4th lecture. We're going to see Bell's inequalities, which are really one of the most sort of profound and fundamental experimental facts we know about the universe. Be about 7 lectures that are going to be about quantum computing, quantum algorithms. Going to cover sort of Shor's algorithm, this famous thing that lets you factorize numbers exponentially faster than a classical computer can do, as far as we know. There'll be about 6 lectures on more sort of actual information-y parts of quantum information. So things like entropies, and quantum channels, and quantum Shannon theory, stuff like that. 3 lectures, quantum error correction, which is this amazing phenomenon that is really the one reason why quantum computers actually might ever be possible in practice is that you're magically able to correct infinitely many possible sources of error with some finite error correcting scheme. Finally, we'll have another 3 lectures on implementing quantum computers in practice and how you do that. And then the last lecture that I will give will be on specifically on entanglement. In fact, it's going to be on sort of the operational definition of quantum entanglement. In terms of assessments, we're going to have some homeworks. There'll be regular homeworks, but these are really just intended to help you learn. Okay, the grading will be marked based on completeness rather than correctness. If you really make an effort on the problems, you will get marks. So just use it as an opportunity to learn and get feedback and so on. There'll be 2 midterms spread through the course. These will be 25% each. And finally, there'll be the project for 40%. Okay. Awesome. So final thing before we really get started is books. The main book, which is available online, I include a link in the syllabus. It's going to be Wefel and Pollock. It's called A Gentle Introduction to Quantum Computing. It's a pretty good, accessible, introduction to the topic. There'll be homework questions taken from there and so on. The other book that I recommend if you really want to delve deeper into the subject is Nielsen and Chuang, Quantum Information and Quantum Computing. And that's really the Bible of the subject. That's the anything you want to know, at least anything that was known around 2001 or something when the book came out, will be in that book. There has been a lot done, it's a new, fast-growing field, so there's been an awful lot done since then. But yeah, it's a really good reference for any basic facts you might want to know. Okay, so let's actually start on today's lecture. So today, we are gonna, introduce ourselves to quantum mechanics. We're gonna start with the most basic building block of quantum mechanics, which is a qubit. We're gonna cover sort of the basic postulates of quantum mechanics, the assumptions you need to make that sort of underpin all the other results you can derive. And there'll be a lot of it that's kind of abstract and just playing around with maths and seeing some results happen. But we will talk about a physical example of a qubit, which is going to be called photon polarization. Okay, so let's just start with what a qubit is. So start even simpler than that. In fact, let's start with a classical bit. I'm sure you're all familiar with it, but it's just state of a classical bit is given by, you can call it x, just some number that is either 0 or 1. Right? We don't have to call it 0 or 1. We could call it A or B. We could call it anything we want. But there's just 2 possible distinct states, and that's it. That's a classical bit. Okay. What about a qubit? Well, in some ways, the way you describe the states of a qubit are similar. So we have a state that we call the 0 state that we write like this, and a state that we call 1 state that we write the same way. So these weird, asymmetric angle brackets are called a ket. You will see to some degree why in just a minute. but this is really just, it's just notation. We just have two states that we've given arbitrary label of 0 and 1 in analogy with the fact that they're standard labels for a classical bit. But they're just two states. But for a qubit, we can also have a whole lot of other states. In fact, we can have infinitely many other states. We can have any state that we could call label psi that can be written as alpha times the 0 state plus beta times the 1 state, where alpha and beta here are just arbitrary complex numbers. Okay? Why complex? That's just the way quantum mechanics works. You can do it with real numbers and you get a different theory that does not describe the universe. The universe likes quantum mechanics sometimes. Sometimes it likes, the universe likes complex numbers sometimes. Sometimes it just likes real numbers. Okay, so what does this mean? It means that the states form a vector space, right? Oops. I can't spell. Form. Right, anytime you can take, you can multiply things by scalars, in this case complex scalars, it's a complex vector space, and you can add things together, then you have a vector space. That's just a mathematical structure that you have. So there's one thing I sort of glossed over here about what states are, is that if I have two states that have different alphas and betas, it's not actually guaranteed that they're distinct states. We have sort of an equivalence relation. Different combinations of alpha and betas can be equivalent to each other. Specifically, if I have state psi, and then I have another state that's lambda times psi. So if psi is alpha 0 plus beta 1, this would be lambda times alpha times state 0 plus lambda times beta times the state 1. We treat these two things as the same state, okay? So really, quantum states are what's called rays in this vector space. The lines going out from the origin. In particular, that means the origin itself is not a state, right? The 0 times state 0 plus 0 times state 1, that's just not a quantum mechanical state. Okay? If you're from a very mathematical background, you can also think of these rays as being points in complex projective space. You're welcome to do that. You're also welcome not to do that and to think, what the hell did the professor just say? What do those words mean? And just forget I said them and never think them about them the same. Again. Okay, in fact, the states are more than just a vector space. They have a bit more structure to them. In fact, the states form what's called a Hilbert space, which is again a fancy mathematical sounding word. All it means is that they form a vector space that has what's called an inner product on it, right? Which is really just a generalization of sort of the dot product that you're familiar with in 3D, right? It's some, yeah. So what is inner product? It's a map that takes in two states, right? So call them psi1 and psi2. These are just two arbitrary states in this Hilbert space. And then it just maps them to a complex number. Okay, we write the thing it maps them to like this. So you can think of this as contracting the psi1 and psi2 as like column vectors. And this is contracting a column vector with the dual row vector. So this sort of psi1 with the reflected, a reflected angle brackets thing around it, we call in quantum mechanics a bra. This really just means a column vector. So this is just the, so the bra means a row vector, ket means a column vector. So this is sort of row vector that's dual to psi1, and then this thing, which is just a complex number, is called, wait for it, a bra ket, right? Because it combines together a bra and a ket, and it's a terribly funny pun because it sounds like bracket. Yeah, there's a great question in the chat that if the sort of the origin of the vector space is not a possible state, then how do the states form a vector space? Yeah, so it's a great question. The states are arrays in the vector space. They're not the vector space itself. Okay, is that clear? So you have a vector space, you have a Hilbert space, and then the states in that Hilbert space are associated with rays, i.e. lines going from the origin out to infinity. Okay, hopefully that's clear. Okay, so for this sort of map from, that takes into two states and outputs a complex number, for it to be sort of actually called an inner product, for all the sort of intuition you have about dot products to make sense, needs to satisfy certain properties. Okay, in particular, well, it's 3 properties needs to satisfy. Needs to be what's called conjugate symmetric, which means psi1, psi2 has to be equal to psi2, psi1, except it has to be equal to the psi2, psi1 bar, right? The complex conjugate of psi2, psi1. Okay, so that's property 1 it needs to satisfy. Property 2 is it has to be linear. So psi1 times some linear combination of psi2 and psi3 has to be equal to alpha times psi1, psi2 plus beta times psi1, psi3. Okay, again, this should be a very familiar property of the dot product, but we take it as the axioms of what this inner product needs to satisfy. And the final property is that psi, okay, which from property 1 has to be equal to its complex conjugate, so it has to be real, has to be strictly greater than 0 for all non-zero psi. Okay, for all psi that aren't the origin, then they need to have, this is called the norm, formerly the norm squared, I guess, and every state needs to have a non-zero norm for this map to be well defined as an inner product. Okay, so that's very abstract, but for a qubit, then we sort of conventionally define 0, 1 so that the inner product is just a very simple concrete thing. So that the inner product of state I with state j, where I and j are 0 and 1, is just delta ij. Okay, so these two states have an inner product with themselves that's 1, inner product with each other between the two that's 0. They form an orthonormal basis. Once we have this inner product, then it turns out it's very natural to use our freedom to sort of redefine, replace psi with lambda psi without changing the state. Okay, so if we replace psi with lambda psi, then the inner product of psi with itself goes to modulus of lambda squared times the inner product of psi with itself. So what we can always do is we can always choose lambda so that the inner product of psi with itself, its sort of norm, its length, is 1. Okay, and conventionally in quantum mechanics, we're just always going to do that. So we're always going to think about quantum states as being normalized vectors in this Hilbert space. So this is called This is called normalization. It's important to note that this does not fully fix lambda, right? I can still have a lambda that's not equal to 1 that doesn't change this normalization, because I can have lambda just be what's called a pure phase, right? Then modulus of lambda squared is 1, even though lambda itself is not equal to 1. So this, you still have distinct normalized states psi that actually correspond to the same quantum mechanical state, but it is still convenient to just assume that we're defining psi to have norm 1. Okay. So this is the state space of a qubit that we've defined. So I'm just briefly going to comment on sort of some differences. Similarities between sort of the very simple bit we had at first and now the qubit we have. And they're basically obvious observations. First is that there is indeed infinitely many possible states of the qubit, right? Whereas for a bit, there really is just 2. So this might seem like a qubit is just like a vastly bigger, why are we even comparing it to a bit? One has infinitely many states, one has 2. The reason we're comparing them is that the qubit still has 2 linearly independent states, right? Any state can be written as a linear combination of the 0 state and the 1 state. And it turns out this is the more meaningful, sort of more significant point. So really we should think of a qubit as only having two independent possible states. It's just you can have superpositions of them. You can have it sort of be both of those states at once, but there are fundamentally only 2. Okay. So everything I've just said can be condensed into what I'll call postulate number 1 of quantum mechanics. I should say that the sort of list of postulates of quantum mechanics is completely non-standardized. Some people will have like 6 of them. I'm only going to have 3. Like the content of them is standard, but the way they're grouped up and so on and exactly what gets included is not. So postulate 1 is states in quantum mechanics equals rays in a Hilbert space. Okay, so that just summarizes everything I said for the last 10 minutes or so. The one other thing I'm going to add is sort of, a bit heuristic. The dimension of the Hilbert space is what is going to correspond to sort of the classical number of states. If you think this second point is like, it's not obvious, like that it has any meaningful content, I sort of agree to some degree, but it's a useful thing to keep in mind. Okay, but the real fundamental part of the postulate is that states in quantum mechanics are rays in a Hilbert space. Okay, so that's all great, but it was all terribly abstract. So, what we really want to do is yeah, at least what I always want to do is I want to have some sort of physical intuition in mind for what we're actually talking about. So what are qubits physically? Like, what actually are these things? Well, let's try a simple question. What are some examples of what classical bits might be, like physically? Like what's the actual thing? It's not just an abstract 0 or 1. What is it? Anyone want to give some examples? Come on, guys. Okay, I'll give us.
Spin halves.
Sorry, say that again.
Spin halves.
So spin half is going to be an example of a qubit. We're just going to talk about classical bits for a moment. So there's an example in chat of something being on/off, which is a great example. Like anything that can be on/off could maybe be a light switch being on/off, right? That is a classical bit. It has two possible states, on and off. Could be a transistor, right? In a computer, it's much more likely to be a transistor than it is a light switch. But again, it's just a switch being on or off. Yeah, great. So those both said in the chat. What about some other examples in computers? How are come on, computer science people, how are physically bits stored in computers? When the computer's running, then it's yeah, so there's an example there of just 0 or 1, right? So that's just in writing, right? It could be 0 or 1 written down and A or B written down. Anytime there are only two possibilities for what could be written, then yeah, that's an example of a bit. Yeah, what about when we're storing something in a computer? Yeah, great example. So a hard drive, right? The bit is stored in the direction of the magnetization in some little region, right? Whether the magnetic field is up or down. What about a CD? Anyone know how they're stored in CDs? The answer for a CD is that they're just stored in little bumps on the surface of the CD. Okay, so that's a whole host of yeah. So those bumps are then read by a laser. So that's a whole host of examples of sort of classical bits. What about some examples of physical things that act as qubits? Okay, so there's one in the chat from Daniel, which is spin. So particularly, it depends on the thing that's spinning, whether the spin is a qubit or not, but the spin of an electron is indeed an example of a qubit. Has two possible states plus superpositions of them. Another example is what you might think of as a spin of a photon, which is the polarization of the photon. These are the spin of an electron and the polarization of a photon are really the same concept. So it's another example of chat of orbital energy of an electron. So in general, an electron could have lots of states, but it's true that you can encode a qubit in sort of two possible states of the energy of an electron. In fact, that's roughly what happens in one of the sort of common ways people actually you make qubits in practice, which is trapped ions, there it's you're just using two energy states of the trapped ion. Trapped ion and electron are pretty similar. It turns out an ion is a lot heavier, a lot more practical. You just use them to be your two states of the qubit. Yeah, great. And another example, probably the most famous one at the moment, superconducting qubits. Which are basically, you can think of them as just the state of a superconducting loop of current. Okay, so the point is that there's a lot of examples. Anything, anytime you have two possible classical states, you have a bit. Anytime you have two possible quantum mechanical states where you can take superpositions of them, then you have a qubit. Okay, so they're really just they're a fundamental sort of logical object that you can physically implement in all sorts of ways. Okay, but the example we're going to talk about today is going to be photon polarization, which, as I say, can be thought of as like the spin of a photon. So some of you may be very familiar with polarization. Some of you may be CS students who have never thought about it at all. So I'm just going to give a very high level picture of how it works. Light, as hopefully you're aware, is an electromagnetic wave. Okay? So it means that there's sort of an oscillations happening in the electric field and the magnetic field that are sort of moving in a certain direction. So if we have our axes, then you can have a wave going along like this, moving this direction. Right, so in this case, the sort of component of the electric field that's getting excited is going in the vertical direction, right? So we would call this, a vertically polarized light. Turns out that you have to have the electric field perpendicular to the direction of travel. It's just a fact about how electromagnetism works. So our two options, well, we can have sort of, the polarization doesn't just have to be vertical, it could be anywhere in this two-dimensional plane, right? Could also have horizontally polarized, or we could have at any angle we like, and so on. Normal light, I should say, if you just like look at the light from your lamp or something like that, then the direction is totally random. And if you sort of look at it for like a tiny fraction of a second, then the direction will change. The electric field will change all over the place. However, if you pass that light through a polarizing filter, then only one component of the electric field survives. And you're left with an electric field that has to be in some particular direction. Great. Okay, So I really want to emphasize that when you pull out a polarizing filter and look through it and see that the light is dimmer or whatever, that is a completely classical phenomenon that is well described by classical physics. There is nothing, you don't need quantum mechanics to understand that. People understood polarization of light long before anyone had heard of quantum mechanics. But what you can do is you can imagine making that light source dimmer and dimmer and dimmer and dimmer until you only have one photon left. So you just have a single photon traveling along, and then the polarization state of that photon is described by a single qubit. Okay, that clear to people? So for example, you could have that qubit be vertically polarized, which I will write notation like this. People use different notations. Just up down to signal that it's polarized in the vertical axis. So this means that the qubit is traveling in some direction. Its electric field is going up and down vertically. Okay. You could also imagine another state where instead it's horizontally polarized, i.e. it's oscillating in the sort of left-right direction. Okay. And it turns out that, as you might guess, I guess, these two states are orthogonal to one another. So if we normalize them correctly, we can think of them as forming an orthonormal basis for our qubit states. But we can, of course, have all sorts of other states. We could imagine, for example, vertically polarized plus horizontally polarized, right? So anyone see a problem with the state I just wrote? Or some way we might want to correct it? Great. Someone said no, it's not normalized, right? If I work out the inner product of this state with itself, I'd get one from the vertical part, inner producting with the vertical part, and one from horizontal with horizontal. So we get 2. So to make this normalized, we have to divide through everything by the square root of 2. So we take its inner product with itself, we get 1. Okay. Again, we can think of the unnormalized state as being completely fine, but it's just convenient to talk about the normalized state. Okay, so imagine we take this vertical electric field and we add a horizontal electric field. What do we get? Well, we get one at 45 degrees, and magically turns out that indeed this state, that's completely classical, but it is true that taking the superposition of the vertically polarized and horizontally polarized qubit states, we get what you might call the 40 down left to up right diagonally polarized state. Okay, so this is a state where you can think of, everything is quantum mechanical, so these classical pictures are a bit dodgy, but you can think of the electric field as being at 45 degrees upright to down left. Okay, we could also imagine instead having vertically polarized minus horizontally polarized, and this one will end up being the opposite diagonal, right? Up left to down right. And you can just check explicitly by linear algebra that the inner product of these two states is again equal to 0. Okay? So these again form an orthonormal basis for qubits. It's just as valid. you know, we could have interpreted sort of the up-down state as 0 and the horizontal state as 1, but it would have been equally valid to say that the down left to up right state is 0 and up left to down right state is 1. Okay? Any orthonormal basis is sort of equally valid to any other. It's just often convenient to call some particular basis 0 and 1. Okay, so that's great, but what about, you know, we're allowed to take complex superpositions of states in quantum mechanics, right? So what on earth would that mean? What about the state, for example, 1 over square root 2 up down plus I times horizontal? Anyone know what that state corresponds to? So what the classical version of that state is? So what does multiplying by I mean in the context of a wave? It means you need to add a phase. Right, so someone said it in the chat. So I times this horizontally polarized state we should think of as being like a state where we have the same sort of electric field, but we've applied some phase to it. So now it's, rather than starting at the origin, it's starting to the left, and then it's going to the middle, right? If we add this electric field to our original vertically polarized one, what you get is an electric field that looks like spirals. My artistic skills not good enough to do this very well. But what you see is it spirals around in circles, okay? So we call this circular polarized state. I'm going to use this notation for it. And similarly, we could have minus I rather than plus I. Again, these two states would form an orthonormal basis. And this one looks like a circularly polarized state where it's rotating the opposite direction. Incidentally, anyone know some examples of circularly polarized state in practice where they show up?
3D movies.
Yeah, great. Not something, I was going to say, it's not something you might have experienced in the last few months, but probably in the last few years. When you go to 3D movies, then one eye will be, has a polarizing filter that allows through circularly polarized states going around in one direction, and the other one allows them going the other direction. Because these two states are orthogonal, then none of the wrong type of light gets in each eye, and everything works. Okay. Okay. So classically, any two sort of distinct polarization states can be distinguished, right? If I have sort of, you know, light that's polarized in the vertical axis and then light that's polarized 5 degrees off the vertical axis, then I can just measure the electric field. I might have to do a moderately precise experiment, but I can tell the difference between two of them, okay? Turns out we're only really able to do that because we're cheating and we're using the fact that there's this really, really large number of photons in everyday life, okay? If I only have a single photon, then I can't do that. I can only perfectly distinguish two states if they're orthogonal. And this is going to lead us into our second postulate for the day, which is going to be the measurement postulate, which is the weird one. You know, the crazy thing of quantum mechanics, which is the rules on What quantum mechanical states are possible to distinguish and how? Okay, so we're going to give a slightly more advanced version of the measurement postulate next lecture. But this one will do for now. It certainly is enough for any measurement you might want to do on a single photon. Which is that for every measurement there's going to be a corresponding orthonormal basis in the Hilbert space. I'm going to call that those basis states. I'm going to label by M for different possible values of M. Each state in the basis corresponds to a measurement outcome. Okay, but you might ask, what if my quantum mechanical state is not in that basis, right? It's a superposition of different states in that basis. Then what you find is that the probability of getting outcome N is going to be given by the modulus squared of the inner product of psi with M. Okay, that's just the rule. It's called Born's rule. It's sort of crazy, but it's, that's how quantum mechanics works. It's incredibly well experimentally verified. So that's, call this A, call this B. Part C is sort of even more crazy in some ways. After doing the measurement, the state will no longer be in the state psi. It will actually be in the state M for whatever outcome M you happen to get. Okay? This is sometimes called, I really hate this term, but it's the standard one for historical reasons, collapse of the wave function. Wave function is a term used to describe the quantum state that makes more sense in sort of infinite dimensional quantum mechanics, like particles and stuff, than when you're talking about qubits. But it just means the state. It means you've taken the state and you've collapsed it into this new state M. Okay? So let's think about this a slightly different way. Given any state psi, we can expand psi in terms of this orthonormal basis, just as some numbers that are called Cm times the states M, right? That's just expanding a state in basis, the orthonormal basis. It's completely standard. You can always do that. Then this Pm, in terms of these Cm's, it's very easy to check. It's just equal to the modulus of Cm squared. Okay? Question you should be asking is, how does this make sense? As if these are probabilities, they have to add up to 1. Why do they add up to 1? Can anyone tell me? Yeah, after orthonormal basis, it says state M. Yeah, go ahead. Sorry, I was just
They're normalized.
Great. So we've assumed that the state psi is normalized. We've written it so that it is normalized. Inner product of psi with itself in this basis, just a sum over M mod C squared, sum over M. The probability of getting M, so this is equal to 1. So this sort of makes sense as a rule, other than the fact that it's like really weird and unintuitive and crazy that this is how measurements work and they affect the state in this way and so on. It's at least consistent that those are probabilities. Okay. Okay, let's apply this to our polarized photon. Okay, let's imagine we have a state psi that is going to be vertically polarized initially. Okay, and then we're going to measure, and we're going to do a measurement that corresponds to the basis vertically polarized, horizontally polarized. Right. Now, what do we find? Shouldn't need to do the maths in full for this. It's pretty clear. The state is normalized, so its inner product with itself is 1. So the probability of finding that it's vertically polarized is 1. Probability of finding that it's horizontally polarized is 0. Okay, so everything is sensible, great. But that's not the only measurement we could do, right? We could also try to measure whether it's diagonally polarized, down left to up right, or diagonally polarized, up left to down right. Again, orthonormal basis, it's a reasonable thing to measure. Then we find the probability of getting down left to up right is modulus squared of this thing with up. This diagonal state was 1 over square root of 2 times up plus 1 over square root of 2 times horizontal. So this is 1 over square root of 2 squared, which is just a half. Okay, and then by process of elimination, that means the probability of getting the other diagonal is also half. This doesn't seem too weird, right? We wanted to know whether which diagonal it's on, and actually it's like halfway between them. It's 50-50, which it ends up being. Now I'm going to make it weird for you. We're going to now take the state after we do this measurement, and we're going to again measure whether it's vertically polarized or horizontally polarized. Okay, so we need to consider the two cases. Case 1, we measured previously and got that it was diagonally down left to up right. So psi is in this state. Then, in that case, probability of getting up down, vertically polarized, is going to be the inner product of that state with itself, modulus squared, which we just found out was a half. And so similarly, the probability of getting horizontally polarized is also a half. Case 2, which also has 50% probability of being the case, is that we previously measured and we got that it was diagonally polarized the other direction. Works out exactly the same. Again, we find that it's a 50% probability of getting vertically polarized, but also a 50% probability of getting horizontally polarized. Overall, we find just 50-50 each possibility. So I really want to emphasize how totally crazy this is. We started with a state that was as definitely vertically polarized as we possibly could have it be. And then we just try to measure it in some other basis. And then just the fact of having done that measurement means when we then measure it in the sort of ordinary basis where we thought we knew the answer, we now only get that answer 50% of the time. We're just as likely to get the sort of opposite answer. So yeah, as I say, this is crazy, but it is also an experimental fact. And in fact, if you're willing to ignore the fact that the light source in this room is pretty classical, and so we're not really we're talking about some very large number of qubits, and so there are classical explanations for it, then it is an experimental fact that we can observe right now. Okay, so I have here them linearly polarized polarizing filters. Okay, so what this filter is doing is it's only allowing light to come through if it's polarized in a certain direction, right? It's like you can think of it as doing a measurement where it measures whether it's polarized in that direction or the orthogonal one. And then if it's the orthogonal one, it absorbs it. If it's the right one, it lets it through. Okay. So I can now put two of these things, and if they're oriented the same way, then they let the light through because it measures it once, and then it's in that state, and then it just gets allowed through with 100% probability. But as I turn it, we're now measuring a different basis. It's slowly getting darker. When I turn it completely 90 degrees, then no light gets through because the first polarizing filter puts it in the orthogonal state, and so with 100% probability, it gets absorbed. Okay? So there's no way for light to get through here. But now what I'm going to do is I'm going to add this third polarizing filter, and I'm going to put it between the two, and I'm going to put it at 45 degrees. Okay, so this is going to do a measurement in the diagonal basis, and it's going to let it through in one of the two outcomes. What I then claim is that magically you can see my face again. Okay, because the fact of that intermediate measurement happening means that the state is no longer vertically polarized, say, and so it's then able to get through the horizontally polarized thing with some probability. I can even, so if I have it aligned with the same measurement basis, doesn't let through, so you let it, turn it a bit, you can start to see my face, hopefully. Turn it again, goes completely black. Okay. So yeah, again, I want to emphasize, you did see quantum mechanics in action there. There were an awful lot of photons, and whether they got through was determined by the rules of quantum mechanics. But because there were so many photons, then there is also a classical explanation. So it's not like on its own proof of quantum mechanics. So yeah, that was just a brief demonstration. But this is really an example of a very general principle, which is that anytime you have measurements that are not in the same basis as one another, then the existence of the first measurement will affect the outcome of the second measurement. Anyone want to know what principle of quantum mechanics that is? It's basically, it's a qualitative version of what's called the uncertainty principle. Normally by the uncertainty principle, we mean a specific lower bound on how much uncertainty you have about different measurements. But there's a sort of qualitative version of it, which just says anytime you have measurements in different bases, then you can't simultaneously have all of them, all the measurement outcomes be known in advance. Great. Okay, so hopefully you guys aren't all too exhausted. We have about 15 minutes left, which is just right to talk about the third postulate of quantum mechanics, which is going to be how dynamics work, which is something we haven't talked about at all yet. We've talked about measurements and how they affect the state, but you can also obviously have the state change without measurements, just because it evolves with time, or someone applies some operation to it, starts hitting with a hammer or something like that. It's going to change the state. Let's again talk first about what dynamics you can have for a classical bit. Anyone know what the possible dynamical evolutions of a bit are? If I have some initial time, the bit is in some state, and then final time is in a new state, what possible rules can I have for how the final state is related to the initial state? Well, basically we have the final state, I'll call y. It's going to be some function of the initial state, right? So the initial state is x. Final state after the dynamics is y. And the function f is going to describe the dynamics or the operation you've applied, or whatever it might be. So what possible functions can we have on a single bit? It's not very many, so somebody needs to suggest one. I think you muted.
The floor function. The floor function.
The floor function. So I would think of a floor function as a function that takes in a sort of real number and outputs an integer, and so it won't really do anything if you put in an integer. So yeah, certainly one possibility, which someone's mentioned in the chat, is just that the function is just the identity, right? We just have y equal to x, right? The state just does nothing. That's still dynamics. They're trivial dynamics, but they're dynamics. Another one someone's mentioned is you could have the bit be flipped, right? So one way to 0 goes to 1 and 1 goes to 0. One way to write this is y goes to x plus 1. Everything is mod 2, right? There's actually only two more functions you can have, which are also basically equally boring, which are just that whatever x is, then y ends up being 0, right? The initial state doesn't matter, and you end up with 0. And final possibility is that y is just equal to 1. These are actually all possible dynamics for a bit. Okay. What about qubit? What can that do? How can it evolve? Well, let's just take this sort of classical example of a bit being flipped, right? So, the sort of analog for a qubit would be that we'd want the state 0 to go to a state 1, state 1 to go to a state 0, okay? But then we have a sort of question of, what about some random state like alpha times 0 plus beta times 1, right? What on earth does that go to? Is it undefined? Do we need to specify it separately? What do people think? Anyone want to throw out an answer?
So alpha and the beta just changes.
Sorry, say that again.
Oh, I was just thinking alpha goes to the eigenvalue of the 1 and the beta goes to the eigenvalue of the 0.
Yeah, great. So it turns out that it can't do whatever it wants. If I just had sort of an arbitrary function on the states for qubit, it could go to anything it wants. But for actual evolutions, it always has to go to alpha times 1 plus beta times 0. Okay, so what happens to all the possible states is uniquely determined by what happens to 0 and 1. Another way of saying this is that evolution of a qubit is given by linear maps. Linear maps you should all be pretty familiar with. They're just matrices, right? So in this case, they're just 2 by 2 matrices. Okay, what about another of the possible dynamics we could have for a bit? We could have 0 goes to 0 and 1 goes to 0, right? This was a function. It was just a function that takes everything to 0. What do you think would then happen, given what I just said, to the state 1 over square root of 2 times 0 minus 1? What would that go to?
0.
Yeah, what it wants to go to is just the origin, right? But I've already said that the quantum states are rays, and the origin is not, sort of part of all rays, but it's not part of any particular ray. So that doesn't make any sense. And in fact, the answer is that this is just not allowed whatsoever. There is no equivalent on a single qubit to the dynamics that take both 0 and 1 to 0. Okay? And the reason for that is that dynamics in quantum mechanics always preserve the normalization of quantum states. Okay, and they need to preserve the normalization of all states, right? In this case, preserve the normalization of the 0 state and the 1 state, but it didn't preserve the normalization of 0 minus 1. In fact, it took its norm to 0. So that was pretty terrible. Okay, so what does it mean for a linear map to preserve the sort of norms of vectors? It means it's a rotation, right? If I had a real vector space, at least it would mean it's a rotation. So in this case, it means that what we have, the dynamics are given by sort of the complex version of rotations. Okay, so if our initial state is psi, then it will always go to psi times some linear map that I'm going to call U. So often in quantum mechanics, I won't always do this, but often operators or matrices have hats on them. Okay, this is just part of the notation along with, you know, vectors being written with these funny angle brackets around them, then operators have hats put on them. So yeah, so our dynamics are linear, so we have psi going to U of psi, but we also need to preserve the normalization. And that means psi will go to, well, the ket psi goes to U acting on psi. What about the bra psi? What's that going to go to? Right, the bra is like the row vector dual to psi. So what it goes to, the dual of U of psi is psi followed by U dagger, right? Where, remember, U dagger, just a transpose. Just because we're going from a column to a row, we need to take a transpose. And we also complex conjugate. Okay, and again, that's just because that's how the inner product works, right? You contract the state with the row vector complex conjugated. Okay, so you need it to get my property 1 that I said initially. If this is true for all states psi, yeah, so we need to preserve normalization, we need to have that for all states psi, then this has to be equal to this. It has to be equal to 1, right? If this is true for any state psi, then it just has to be the case that U dagger U is equal to the identity matrix. This is the definition of a complex rotation. The formal word for it, which hopefully many of you are familiar with, is a unitary matrix. Okay, so postulate 3, quantum mechanics, our last postulate for the day. Dynamics are unitary. Okay. So I'm not going to say too much about this. I'll say a lot more in the 3rd lecture. But let me just briefly comment. We saw already that there were examples of classical dynamics, right? Like both states going to 0. There's a question in the chat of why must normalization be preserved in the dynamics. This is really just a postulate, okay? I'm just claiming to you that this is, you know, an assumption you make that then leads to quantum mechanics, which is then being experimentally verified. There's not some deeper derivation why it's true. So the example of 0 and 1 both going to 0, which would be a like non-invertible singular matrix. You know, we saw that didn't really make much sense. It was taking a state to something that wasn't a state at all. But the reason normalization means to be preserved exactly is just it's an axiom of the theory, okay? And I refer you to every experiment ever that has verified quantum mechanics for why it's true. Yeah, so we saw that sort of some of the classical evolutions weren't possible to have with unitary matrices when we sort of upgraded them to quantum evolutions. And in fact, they're only possible only allowed when the dynamics are reversible, i.e. when the function mapping input to output is invertible. This is going to play an important role when we come to quantum computing. Okay, why is this? It's because unitary matrices have U dagger U equals the identity, so U dagger is U inverse, so they're invertible. Okay, so any sort of classical dynamics they might try to describe will have to be reversible. Comment 2 is that there are a lot more examples of possible quantum dynamics than there are reversible classical dynamics for the sort of basis of 0, 1. Right, in particular, there are infinitely many 2 by 2 unitary matrices. We have a lot more freedom with the quantum dynamics that we're allowed. So for example, we could have a U that takes the 0 state to sort of 1 square root 2, 0 plus 1. This is something often called the plus state. We often use that notation. It takes the 1 state to 0 minus 1. Right, this takes an orthonormal basis to an orthonormal basis, so it's unitary. But it's not in any way yeah, so by classical dynamics, I just mean functions on a bit. Or we could have more than a bit, we could have d possible states, right? And we could have functions on that take zd to zd, right? That take these d possible values to themselves. Yeah, so we have infinitely many unitary matrices, and all but 2 of them take 0 and 1 to like something that's not 0 and 1, right? To a new basis. And so that just doesn't have an equivalent for a classical bit. Okay, so that's really all we're going to say today. Lecture is about to end. I'll just make some comments about the next few lectures. So next lecture, we're going to talk a lot more about postulates 1 and 2. Going to talk in more detail about the space of states of a qubit and what that looks like. Going to talk more about measurements. And then lecture 3, we're going to talk more about postulate 3. Okay, so if you're still finding this new and unfamiliar, maybe you haven't seen quantum mechanics before, don't worry. There will also be homework 1, which I'll try to put online later today. It will be due next Friday. Should be pretty easy, accessible-ish questions to sort of get you familiar with new concepts. You know, I say easy as in once you're familiar with conceptual framework of quantum mechanics, it's easy. Getting familiar with the conceptual framework of quantum mechanics is itself quite hard if you haven't seen it before. So, you know, I'm not saying you should find it easy if you're seeing quantum mechanics for the first time. But the real point is that you guys are going to have time to get familiar with this stuff. If it seemed like we were seeing a lot today, it's because I wanted to introduce the whole framework, quantum mechanics, and then we can go into more detail and stuff in future lectures. Okay, so yeah, I think you are all free to go. Thank you for coming. See you next time. Yeah, all the best, everyone.